when a particle crosses them, it will bend in a kind of funnier way, which is a little bit harder to just do simply. But it's going to bend. If it's going straight out to the muon detector, this is muons here. If it's going straight out to the muon detector, it should bend like this, right, or like this, depending on the charge. However, this is not always going to be just the XY plane. It's kind of the plane of whatever direction the thing is going, which may take a little bit of math for you to look at. Okay. Or just, clever approximation. Just kind of like, oh, look, if I put it like this, I can figure out about how it works. And that's fine too. That still some three dimensions? We had the day, I know. Did they add it yesterday? You could also try and just fit it directly with a program that'll do it. Well, from Alpha, I think will. I'm not sure at that, but definitely should. So that's another possibility, just try and fit it directly. Here's the other thing. The toroids have a non-constant magnetic field. Okay? It varies. The good news is it varies only a small amount. So you can get close to it. And I set it so that the number you gave me is the number that's right in the middle. So you will probably get a little bit off on the toroids, but it should only be a little bit. Because it varies with the radius from the center of the cylinder here. So from here to here is not actually that much change because it's a big radius to begin with. Nonetheless, you may get some. You may get it not to fit that well, and that's normal. If you can try and, if you want to impress me, then you can try and calibrate for that. In other words, I come out this much low on my muons, so I'm going to try and bring that much to compensate. That would be impressive. Just saying.
Calibrations.
Okay, so that's the tracking people. So the tracking people, you have to be aware you can only measure in 2 dimensions, right? Because that's the only curve in 2 dimensions. The other dimension is not something you can measure in. Then once you have those measurements, then you do want to eventually try and combine them together, right? Because whatever comes out here, I guess it should be something that came out here and then went straight and then went that way and then bent again, right? Depending, of course, on how you have everything. Because if you have your magnet outside, then that will change. That will change things, right?
Oh yeah.
So calorimetry people. Calorimetry people are generally fine. You're going to get a cluster of energies, though. Okay. So for the tracking people, you're going to have to turn your hits into tracks, right? Which is probably easiest to do by eye. Just to look for the ones that go together. Hopefully you have enough layers in your detector that it's easy to see. I was nice. I gave your detector 100% efficiency, so you don't have to worry about things mysteriously missing. You may see when particles go through anything, they start to shower, right? And so that includes like the beam height, right? So as they start to shower, it'll just be a little bit, but you may see small clusters of hits instead of a single hit. That's because the particle is starting to shower, and so it's hitting several strips at once instead of just one. As it passes through the silicon, it's very thin, but it will still shower a little bit at least. So you may see that. I say may because I haven't actually run the program yet, so I'm not sure. But you might. Or you may see nothing at all. But I think I have a good enough programmer to make something come out. Calorimetry people, you're going to see clusters. That's what we call them. Okay? A cluster is when a particle hits and showers. If you think about it, your calorimeter. This is like the particle's coming in this way, right? Your shower comes through the calorimeter like this, but your calorimeter is divided up like this, right? So what you're going to see is, I'm going to make up some numbers. You're going to see like, 25 and like 12 and 12 and 2 and 9. In other words, you're going to see numbers, a high number in the middle, and then decreasing numbers on the sides, right? It's not going to be in a single, we call it a tower, okay? A single piece of your calorimeter. Remember that segmentation you did? That's probably not going to be in a single piece. You're probably going to see it in that and several adjacent pieces, depending how finely you segmented your calorimeter. So you need to identify the cluster, right? And the energy of the particle is going to be, gotta guess? you add up all the energies of the cluster. Right? So you add up all the ones in the cluster, then you get an energy. That makes sense, right? Now, the electromagnetic calorimeter I have made 100% efficient again, because they're close to that. But hadronic calorimetry is never that good. Okay? Hadronic calorimetry, as I mentioned before, is really bad and hard to do. And so I was nice. So what happens is a lot of energy gets lost. It does not go into scintillation light. It gets absorbed or into showering. Instead, it gets absorbed by nuclear interactions. The nucleons vibrate and then kind of settle down, and it gets released as heat, and we can't see it. So because of that, you always lose energy in hadronic calorimetry. That just never gets, you just can't see it. You always measure too low in these guys. Does anyone have uranium?
Uranium?
In their HCal? Did anyone use uranium in their HCal?
On person?
Right there for a second.
Could it be confused there?
No, I mean in their final design. Anyone?
No.
No? Okay. So that's good, because I realized I forgot to account for that, but if no one used it, it's a good point. Check with the other class.
Yeah.
So what that means is you're going, now in real life, every interaction actually fluctuates like crazy on hadronic calorimetry, which is really sucky, and that's why hadronic calorimetry is so hard. But I'm going to be nice to you since you have so little to calibrate on, and I'm just going to drop them all. The energy readout is going to drop everything by a constant amount, which is so therefore HCal people, someone, it doesn't have to be more than one person, but someone needs to get a correspondence. So in other words, if you add up all the energies for the ecal, you should get like your number, right? You should get the right answer. But if you add up all the energies for the HCal, you should get low. And you should use that to calibrate to figure out, okay, this is how much I should be getting out of it. Yes, sir?
So for like working with the tracker and the calorimeter groups, so I just want to clarify, so like the tracker group assembles like a track of particles, and then like the calorimeter group uses that track to maybe like try and get this much energy calculated or like.
Right, so what should happen is the tracking, well, you're going to do it independently probably, and then just match them. Right, you'll say, okay, here's the track, here's the track, here's the track, here's a jet, maybe, right, and things like that. And then the calorimetry people will say, here's a cluster, here's a cluster, here's a cluster, and then you say, oh look, this cluster is some kind of lepton or something. You're like, okay, here's the energy of it. And then the muon people will be like, oh, no muon track, it must be an electron. And you're like, okay, right? Whereas then you're like, oh, that one's a jet, and the calorimetry people will say like, okay, you're getting to the jet, and so forth, right? So usually you'll find them independently and just match them together.
So will we get like pictures or something of that form?
Well, you have an Excel document with XYZ coordinates
for
everything. So you can actually put them all in the same document and see where they all appear. Like you put them on the same graph and you'll see track, cluster, track. Yes. Okay, so jets. Jets cannot be measured well in the tracker because there are too many data particles, right?
Yes.
So because of that, the tracker will see, so a jet in the tracker will look like this, right? A whole bunch of particles going in one direction. And remember, some of them are low energy, so you always have some that kind of like, that spiral out and don't go anywhere. If a particle spirals out and doesn't make it out of the tracker, what does that mean about it? Good, it's low energy, and not that low energy. You guys have some big powerful magnets, if I recall. So, but I mean, you can even calculate that, by the way. It wouldn't be too hard, right? The circle of radius that, you know? But anyways, the point is, you might see those, and that means too low energy, don't worry about it, right? If anything loops around and doesn't make it out of the tracker. So then if you have a jet, you're not going to be able to measure it in the tracker. It's just too hard. So who's going to measure it? Calorimeter will just take the whole thing, right? Which will be much broader than a single particle. Right? There'll be a whole bunch of particles. And we take that all into one big cluster and call that your jet energy. Okay? That's the standard way of doing it. What the tracking people do have to worry about is to V-tag it. That's to see if it's a V-jet, to look at the tracks and see if they're coming from a different place than the primary vertex. Okay? So that's the colorimeter's job. All right.
That's all we have to do?
No.
Oh.
I mean, it's not too bad.
Yeah, no. I was wondering if there's anything more.
So you have to do it for each regular particle. And
Okay.
you have to do it for the jets. The trackers are not going to do the jets, right?
Yeah.
And then you're also, so the thing I gave you for missing ET was not really the way you calculate it. So let me give you the right way to calculate it. I realize that. It's not like it was the wrong definition, but it's not the way to calculate it. So let me give you the right one, okay?
Write this down.
Don't tell me to do.
Write this down.
So the ET of A, okay, this is how you calculate the transverse energy of a tower. A tower is a piece of your calorimeter, okay? And the transverse energy of a tower is, wow, why is this so hard? Hang on a second.
Wait.
There we go. Is the energy times the sine of theta. Yes. Where this is for the tower. Okay? Every tower has a position, right? I give it to you in x, y, z, but you can easily convert that into theta. In fact, let me give you that conversion.
Okay, because he told me.
You might not know this one.
Listen to your dad.
Okay, so for the calorimetry group, get that down. Actually, probably a few others, we just in case. Right? So this is how you can calculate theta from x, y, z. Spherical coordinates, you'll learn them sometimes. So I will give you, the things I give you are always the coordinates of the detector, not of the particle, right? I'm not telling you where the particle is, I'm only telling you where your detector gets hits. That's another thing that can throw you off, especially in the muons. If you have a really widely spaced muon detector, then you will not get a nice curve, right? You will just get, your points will be the nearest points that muon happened to hit. You see? So something to look out for. Okay, so you calculate this. So this is for the tower. In other words, not for the. So you can just get this directly off the coordinates I give you. You do not need to do anything fancy with the particle. You can just take the coordinates I give you and find this factor right away, and then multiply by E for that tower. And then the total ET is the sum of the tower ETs. The sum of the tower ETs plus, well, yeah, and then the missing ET. Remember, the missing ET is going to be negative the total ET. Sorry, one more thing. Sorry, easier than this. Sorry, it's easier, it's better. I just realized, I'm sorry. Long night.
What?
Much easier.
Shit.
Just go to the x and y coordinates of the vector. Okay, ET is a vector. So you just put in the x and y coordinates of the vector. So when you sum as a vector, in other words, you take ETX, ETX1 plus ETX2 plus that gives you the ETX total. You see what I mean? You sum the x and y components separately. Okay, and if you take all those and you take the minus sign of that, you'll get a vector, a two-dimensional vector that is your missing ET. That's where the neutrino is if there's a neutrino. If this number is close to 0, then there's probably nothing, right? It's probably just read out error and stuff at that point, right? But if it's a substantial number, then that means, there was a neutrino. Or maybe more than one. Okay, does that make sense? So you just make two, you make an ETX and an ETY for each one. And each one is just the energy times the x coordinate energy. Hang on. That's not quite right.
Of course not.
It's close though.
Maybe we should all just take a nap. I think everybody can go.
Yeah, of course.
How are we supposed to
Overtry.
correct it? You can't.
are expectations mean?
I think once we
There you
declare
go.
it on the equal
That doesn't-
student.
Still not too bad. This is just this formula, right? Square root of x squared plus y squared plus z squared. That's just how far it is. But anyway, the point is that all the x's and y's are just from the tower coordinates. So all you have to do is plug it straight into Excel. It's ready to go. Okay? Yeah.
I guess this was what you talked about earlier, but like with the calibration data, so like you said you should check it with you, like to see if like the energies are the same.
You should check with yourself. Right? Because you know what energies you gave me.
Yeah.
I'm going to give you back that data. And you say, so if you ask for 20 GeV electron, you should measure the curvature of the thing and get 20 GeV.
Oh.
If you get 19 GeV, probably right down here. If you get 10 GeV, something's probably wrong. If you get 1 times 10 to the 97th GeV, you probably made a unit mistake.
Okay, so you're just like graphing.
Yeah. But do what you're going to do on the final. That's what it is, right? It's like a warm up for the final. Okay, so those were the things that I remember that I forgot to tell you. This is no guarantee. Accelerator people, you don't have to calibrate, and you don't have calibration stuff to work with. You should make sure you are ready to talk about luminosity, interactions like the 4 vectors, Feynman diagrams. And it's not all about the same person, right? You'll be splitting this up, but that's what accelerator people should look for. Yeah.
So you said that like particle showers like make a cluster. So like what's the difference between
Yes. Particle shower is a single particle striking the calorimeter. When it strikes that first piece of lead, it goes like that, right? And then you get a big shower of particles that results in it. Jets are a whole bunch of particles coming from the vertex, right? And so they'll look very different than the tracker. You do not track the particle shower. You're only going to see the energy in the calorimeter. You can definitely see the tracks of all the jet particles. Okay. Are there any more questions related to the final and stuff? Yes.
So how does this get split up individually? Within the group, like each people have certain tasks?
Each person's going to have an assignment, a role that I will give to the group overall. You can split them up yourself.
Oh.
You shall give me. I could do it that way. It's not out of the question, but I'm not going to. Yeah. I will let you guys decide it yourselves. On the day of the final, it is not expected to be like an exam. It is expected to be noisy and chaotic. I encourage you to talk to each other and to help each other and to have the internet help you and to, and to get things done as best and as rightly and as accurately as you can, whatever means necessary, excepting don't bring in anyone outside of the room, please.
So wait. You said we could use the internet, right? You said we could use the internet, right?
Yeah.
So
Don't ask
Use the
anything.
internet,
Don't ask
not
anything
use
past
someone
that.
who is outside of the box. So don't call up Dr. Lincoln. And
Dang it!
Hey, Don,
why did you have to bring it?
Why? Mike, I know 2 physicists.
So why?
I have to go 6 years time to read the exam. Yeah.
I was thinking AOLE. Nobody uses
I
that anymore.
had my plans.
I would like the grades on this to be high.
Word physicist.
I would
Gonna
like-
bring in.
You could still bring him in, just on campus.
No, I was going to
I think they should be high.
He's a part of it.
Let me ask this. Emily asked a question that's probably on several people's minds. Like, are the grades on this low or high is basically her question. And the answer is, I would like them to be high. I don't give them away for free, but you can show me that, I want you to show me that you deserve a high grade, and I'll be happy to give it to you. Please, one thing I can tell you, put down as much stuff as you can. Okay, this is not one of those ones where you can lose points for putting down too much. Actually, maybe that's possible in some ways. But anyway, in general, put down as much stuff as you can. Put down what you're thinking or what you're working on, or copy the Excel sheet or something, because otherwise I have nothing to grade on, right? So don't just say, I looked at this and the answer was fine. Like, tell me what happened, what you did. That's an important part, okay? Yeah.
It's like the assignment, so you can professional, how do you grade it?
I am giving your group several different assignments to split up. So your group is 4, right? So I'm going to give you 4 things to do, and you can just decide which of you does what. So I'm telling you ahead of time in general what has to be done, but I'm not telling exactly what has to be done in advance because I haven't decided yet. Yep.
So, like last week, so you said that like the transverse energy was like PT over the magnitude.
Yeah. That's the transverse energy of a particle, but that's not actually how we measure it. I realize. So this is how we actually measure it using the calorimetry.
Okay, so then does that mean we don't really need to know how to calculate the magnitude of P? Like, is that just useful?
Because we do most of our stuff in PG. We don't do almost all our work in PG. So
What's the conversion rate for GeV?
about Facebook Messenger.
My God, what's the conversion rate for
That's what AOL Messenger is. It's an ancient program that has been used by his generation.
Nobody has a conversion rate for TeV to GeV? I think it's like
I think I'm going to split the final 50-50 between test and project, or exam and project.
no.
So, in general, that should bring your grade up. And overall, it should bring your grade up to do well in the final. So I encourage you to do well on it.
Oh, yes.
That'd be anything to do. But remember the point, you're not memorizing it. You're trying to figure out what's going on, right? I think you can go ahead if you want in your group to sort of have different people prioritize certain things. It's probably a good idea. Nothing wrong with that. Yes?
So how would the analysis, would one person go to the analysis after we like decide our goals?
Yes, good point. I forgot about that. Yeah, and that might exclude Accelerator because they're already doing kind of analysis stuff. So that will come out on the day, and you'll decide right away.
So will we only have 3 roles then?
In which case, you had 3 roles plus the analysis role, right? Yeah. And I'm still working out the details of exactly how that's going to work. Okay? Any other questions about the final? Yeah.
How do we escape it? I'd rather not see a counselor.
I mean, you have your own tracking curvature to do, right? Yeah, you wouldn't do the tracker, the tracker would do the inner tracker job, right? You have to do the neon tracker.
I feel like it would be inferred.
You should do it yourself separately, and then you should try and match the particles together, like identify this is the same as that, and then you can compare answers.
And he just
Traditionally, the muon tracker is a better measurement because it has less interference and a wider range. On the other hand, you know, that's not necessarily true, so I'll let you guys decide what you're going to do if you have 2 different answers. Yeah. Are you going to be applying relativity to this? Everything's relativistic here. Now, are you going to actually have to use it that much? Well, you should know e squared minus d squared. That one will work. I'm giving you everything in SI units because we measure in SI units, you know? So you have to do a conversion to GeV, which is easy, right?
Especially since we have
for you. You'll want to know things like e squared minus b squared equals m squared. I mean, you should know that one. But like, you know, there are certain people who are going to be doing, probably the accelerator group, going to be doing stuff with 4 vectors. There are people who have to do all the Feynman diagrams and stuff like that, but it kind of depends on what the job is. So your particular job may not involve any relativity at all. In fact, the majority of them will. It explicitly not explicitly involved. Okay? Okay? Okay, well, we'll see what happens. So, let's talk about a few extra things. One of them, I totally forgot to tell you about. It's not like that. It's just like, wow, I never explained this.
Feynman?
Yes, North Korea. So the no, let's see. Oh, I can mention that too, actually. Not North Korea. there is one little one postscript to our discussion of nuclear weapons from last week. I left off by talking about the most devastating devices man has ever conceived. Not conceived, we conceived of course. But the most devastating devices man has ever constructed, right? The fusion bombs, which have a incredible phenomenal yield and are only really useful for taking out large pieces of the earth. But there is potentially a silver lining to that, which is fusion is a far, far more efficient source of power than uranium is. Because what's the source, what's the fuel for fusion? Hydrogen. Where do we find hydrogen?
Everywhere.
Where do we? Water. We use water, right? So, if you could figure out how to make a fusion reactor, it would take as its fuel water. And it would take as, and what would be its byproduct? What would be the, well, not oxygen.
Helium.
Helium.
Which we need.
Which is, yeah, we actually need helium for cryogenics. And actually, you're right, there would be some oxygen release as well, which we could handle. You know? Helium is the most innocuous substance on Earth because it floats out of the atmosphere. I mean, I know we said that about carbon dioxide too, but anyway. Yeah.
Wouldn't you still need to keep it at the high temperature that it is? So
we need to maintain it at a temperature. But once the stuff is used up, the byproducts are not fission fragments like you get in uranium rods, right? Uranium spent fuel rods, they call them, right? Rods that are they can't be used in nuclear weapons anymore are highly, highly radioactive to a deadly level, at least right away. And they've got plutonium and radioactive isotopes of barium and strontium and krypton and all sorts of stuff in them. But the output of a fusion reaction would be helium. And there are no radioactive isotopes of helium. And you would get, and there are radioactive isotopes of oxygen, so I suppose it could be activated by neutrons or something. But in general, there'd be no radioactive waste, like there is with the fission reactor. Instead, you would just get helium, which is even useful. And if you let it go, it floats out of the atmosphere, but it's lighter than air. And so it's like not an issue at all. So it is the world's perfect energy source because the fuel is a little bit more abundant than uranium, a little bit. And there's only one problem. We can't do it, that's right. But there's no reason why we can't do it specifically. There's no physics reason saying it's not possible. It's just we have not yet figured out the engineering challenges, which are considerable. The fission reactor was done before the fission bomb because it was actually easier to get a critical mass of uranium, get up carefully up to K=1 to study it. But fusion, remember, there's only one way we make that happen. What was that?
Atomic bomb.
Yeah, we set off another bomb. So you can't use that in a nuclear reactor.
Well,
no, you can't. It doesn't work. See? And you can't make small nukes. That's not really a thing because they work off critical mass. So you can't make a small critical mass because there's only a critical mass. And so there's a minimum size of an explosion for a nuclear bomb, and it's big. So when they make small, what they call tactical nukes, which are like the atomic howitzer, which is it's an artillery gun that fires an atomic shell, atomic warhead. It's still the size of the Hiroshima bomb, which is about as small as you can get. And so you can't use that in a reactor, right? So what do? Right now, the leading plan is to suspend it in a magnetic containment field and get a plasma going, and then just heat up the plasma and get it really, really, really hot until it reaches the sufficient temperature for fusion. What's the problem? If plasma gets that hot, it loses containment. It gets unstable, and then you lose it. It breaks out of the containment field. And they have not figured that part out right now. There's a big international collaboration called ITER that's working in France to build a giant fusion reactor. We make fusion reactors. They just don't reach what they call break-even point, meaning they take more energy and then they put out, which is not helpful. ITER is going to be the biggest yet. It's like $15 billion or something to build this thing. And it's expected that the break-even point is a reactor 10 times the size of ITER. So on the one hand, it may not be something solved in your lifetime. On the other hand, it might. A lot of things happen that people didn't realize would happen. But at the same time, it's a huge technical challenge. On the other hand, if you solve that problem, you can just get rid of all the other energy-related problems, basically. It can't melt down. It's very safe because you can't make these things happen by accident. There's no radioactive waste. It's like a really, really nice system. If you can just and it's 10 times more productive than nuclear power, which is itself 100 times more productive than fossil fuels. Yeah.
Are you saying in the future it's entirely possible we could be powering ourselves with a copy of the sun?
With the what?
Because the sun gains its power through the same kind of fusion
That's
system.
true.
So we could be powering the entire Earth with a copy of the sun?
With a copy of the sun, yes, small copies of the sun.
Wait.
What about my
Why not just use solar power then?
Why don't we just use solar power? Because, that solar power is fine, but this would be a lot more efficient, for example, to work at night.
No. I was saying, like what Benji's thing was saying,
Yeah,
just
yeah.
make a small copy of the sun.
What about matter?
So anyway, there's a bright side to the future as well. We can just figure it out.
That's like 100%.
If we can figure it out, like, fusion generators are crazy good, but very, very hard.
Yes. That's so
You just got to figure out those engineering problems, which are considerable. And if you can, then suddenly no more fossil fuels, no more solar power, no more. You don't have to worry about anything. It's like Mr. Fusion and Back to the Future. All right. the future will be that you have household fusion generators by the year 2015. It turns out they were wrong. Lots of flying cars and the hoverboards. Maybe that thing they call a hoverboard?
No, it's not.
Yeah.
Eden wants to know if you can use antimatter reactions to create a reactor.
You can if you can find the antimatter. You have to find it, rather because if you create it, then it'll just take too much energy to create it to make it worth it. People argue about it maybe as a storage system, like you store energy in the form of antimatter, like for space travel. It's a possibility. Other people believe you might be able to collect it in space because there are a few antiparticles floating around in space, and that's interesting.
Wait, this is the first I'm hearing about
antimatter
this.
is the only thing that we know of that's more efficient than fusion power.
Yeah.
Fusion power is 2.5% conversion, right, which is crazy high, mass energy conversion. But matter-antimatter is 100% efficient.
Yeah.
So it's very, very efficient, but you have to, if you don't have the fuel for it, then it's not efficient.
You talked about black holes being able to split the two things, right? Antimatter and could we
Put a
possibly?
black hole in a spaceship.
No. Well, okay. So they think their particle accelerate creates mini black holes. So
See, but they're too small. They're like the size of electrons.
black holes are dangerous.
All right, let's talk about something else. I want to talk about something about metals. Okay? No, just metals. They're not too heavy. So, metals, as you may know or you may not, but metals look like this. They're a lattice of nuclei. And the electrons, instead of being bound to a single nuclei in a metal, electrons, there's a sea of electrons that just move around. So all the nuclei share all the electrons. This is why metals are conductors, because the electrons are free to move. They just slide right through everything. Okay? Now, of course, they don't move perfectly because there's these things in the way, right? Plus, there's usually impurities and stuff, right? And these things get in the way and slow down the motion of the electron. They take energy out of the electron. And the taking energy out of the flow of an electric current is called?
Resistance.
Resistance. They call it resistance. Okay. So resistance is the big thing. When you have resistance and you try and run current through something, but there's resistance, what happens to the end of the thing? The current goes in, you get less current out, and it gets
Hotter.
Hot. It gets hot. The rest of the energy turns into heat, which is why all electrical appliances get hot, because you're running current through them, and everything has some resistance, and so that resistance gets turned into heat. The things get hot. What's the problem with things getting hot? If they get too hot, what do? They usually, most of the ones we have now will melt themselves first and then cease to work, which is good because the next step would be to catch on fire. So that's still better. Yeah.
So how does superconducting work?
I am getting there.
Dang
Relax.
it.
But this is why your computers are hot. What's the main metal in computers? Copper and silicon. Okay. Silicon is a semiconductor used in transistors. Copper is the world's best conductor. Well, not quite,
Silver.
but it's the world's best conductor that is easy to get. Copper is cheap, and it's malleable, unlike many metals. It's infinitely twistable. Okay? Infinitely, yeah. Yeah, it actually is.
What does that even mean?
It means you can shape copper into any shape.
Do other metals not do that?
Yeah, not every metal is fully malleable. That's the way copper is.
I still don't.
So copper is really useful. We use it in a lot of stuff. Almost all our wires are made of copper. But copper still gets hot, right? And witness your computer still gets hot. They spend a lot of time trying to figure out how to get the heat out of your computer because everything heats up a lot. So now think about those giant magnets they use in accelerators. Okay? Those huge electromagnets. Well, you're running a huge amount of current through there. So if you have big coils of copper around iron, which is how you run it, then what's going to happen?
Things heat up fairly
It's going to get hot. So what you do is you run cold water through the iron, deionized water, so it won't conduct. Run it through, otherwise problems. Yeah, you run cold water. Usually what they do is they put a hole in the middle of the iron and run water through that, and use that to suck the heat off, because iron conducts heat real well, so that works. And use that to suck the heat off. However, there's only so much heat you can suck off, which is a pity, because the higher you turn your current, the higher the magnetic field is. So really, what's the limit on the magnetic field? Yeah, the cooling is really the limit on the magnetic field. If you turn it too high, the wires will melt, your magnet will stop working, and you're just out a few $100 million or whatever, right? So probably only like $1 million or something like that. But so that's the main thing that controls all this stuff, right? It's heat. Heat is your big problem. So Here's what happens. You know what lowers resistance? If we make a plot, this is a weird plot, it's not good like that. If we make a plot of temperature on this, resistance versus temperature plot, okay? As you lower temperature, these things stop moving around so much, and as a result, what do you think? Yeah, resistance goes down, so the particles can move more easily, the electrons can move more easily. So what you get is a curve that goes very vaguely like this, okay? Very vaguely. Okay. Unless you have very special metals. Very special metals which were discovered by accident and really not well understood even today. We understand the metals. There are these weird ceramic ones that we don't get yet. Like at atomic level, we don't understand what's going on. They're working on it. Because we can figure it out to solve a lot of problems. But there's a few metals where it's going down, and then at a certain critical temperature, usually a very low one, it undergoes a phase transition. You know what phase transition is. There's a phase transition here, and it transforms into a different phase that makes the resistance go to 0. Like actually to 0. The reason for that phase transition is that these are all electrons, right? Well, electrons, one of the things that causes resistance is actually the Pauli exclusion principle. Because the electrons kind of bump into each other, right? So you try and pump up the current, now there's a bunch of electrons there, and they start smacking into each other, right? Because they're fermions. Bosons don't have to knock into each other. So, when you get the temperatures low enough, it is possible to get these two electrons to clump together into what's called a Cooper pair. Okay, so it's quite a while for them to figure this one out. But they tend to clump together into a Cooper pair. What would be the spin of this particle, this resulting pseudoparticle?
0.
0 or 1, depending on their spins, right? It would be either 0 or 1. But that means this would be what type of particle? A boson has integer spin. And because it's a boson, what does it not have to obey? It doesn't have to obey the Pauli exclusion principle. So suddenly, once they form Cooper pairs, they stop bouncing off each other and just go right through each other.
Oh, dang.
Because they no longer have any Pauli exclusion principle stuff playing into it. That's obviously an oversimplification, but it's the basics of what happens. And so there's a phase transition at certain metals when the electrons start to form Cooper pairs, at which point then everything starts flowing freely. And you get something where the resistance drops to 0, and this is referred to as a superconductor. So all of our magnets are made with superconductors because superconductors have 0 resistance. And suddenly heat is no longer your problem. What is your problem is basically how many electrons you can fit into the wire, basically. Like there's only so much you can actually fit into it. Eventually a magnetic field will cause it to break down and so forth. But you can drive crazy amounts of current to this and release no heat. Now, only one problem. It has to be down at the critical temperature, below the critical temperature for that to work. The critical temperature, so the most easiest to produce one is niobium titanium. Niobium titanium is also malleable like copper, making it very useful. In fact, did you guys see the bullet, the copper billet? It's called a billet in Fermilab. It's on the 15th floor.
Yes.
You guys see that thing? It's like a thing like this made of copper, and it has little things inside it. It's a copper shell with little pieces of niobium titanium inside of it. And they take it and they stretch it out into wire, which is kind of crazy. They take something that's this big and they stretch it out to 120,000 feet long, which is kind of crazy. And the reason they have all the copper is there is that actually if you're using superconductors, copper is the insulator, which is kind of crazy. But so you get these superconductors and you can run crazy amounts of current through them. So we run huge, 4,000 amps or something nuts through these things, and they don't get hot at all. But they have to be below critical temperature. The critical temperature for niobium titanium is around 3.7 Kelvin.
That's pretty cool.
That's cold. 3.7 Kelvin is cold. What do we have that gets that cold?
Space.
Liquid helium is our best bet. Helium is the only element that remains liquid all the way down to 0 degrees. That there's no solid phase with helium. And so because of that, you can use liquid's much easier to pump than solids, So you pump liquid helium through, and you have to keep on pumping it to keep the whole thing cold enough. And so the Tevatron used to be the world's greatest producer of liquid helium. Now it's LHC. Tevatron stopped doing it. But the liquid helium cooling is very, very important to keep this thing cold. So it's not about cooling. You're not taking heat out of the system. You just have to keep it cold enough for it to be superconducting. If anything goes wrong and some heat gets released, which can happen, then what happens? If any heat gets into it, it becomes conductive, right? Regular conductor, which means resistance happens. With that much current, any tiny amount of resistance makes it get really, really hot. And so what they do is they quench protection on, they call it quench when you go above critical temperature, and they have monitors that watch for that, and then as soon as that happens, they fire they fire heaters actually, so they heat up everything at once so it doesn't twist one part, and then they shut everything off as quickly as they can, and a bunch of liquid helium boils out and shoots out into the atmosphere. But it's helium, so we're fine. And so this is another use of helium. So yeah, this is how superconductors work. We use them for all our magnets. They're expensive, but they're awesome. And by the way, this is also how you also can use the same basic principle to create things called superfluids, which actually the LHC uses superfluid helium. Superfluids have zero viscosity. You guys know what viscosity is? That's like stickiness, resistance to flow. Superfluids have zero viscosity. What does that mean? It means nothing stops it from flowing. So you can do very interesting things, like if you put it in a beaker, it will flow out of the beaker, like over the edge. Yeah, just if there's enough air pressure in the middle, it'll be sufficient to push it off over the edge of the beaker. If you put it in a ceramic container, it'll actually fall through it because ceramics have actually little holes in it, and if something is very hot, it's zero viscosity, it slides right through all the holes. It's very cool. Yes, you can definitely find videos of superfluids. They use this one weird fountain effect. I'm not actually sure why it happens, but and the cool thing is it's a phase transition. So they have a name when there's like a hole, and it gets colder and colder and colder. Liquid helium, it gets colder, 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 and suddenly everything falls through the hole. It's really cool. Superfluids are awesome. They use them at the LHC because it's easier to pump superfluids. The superfluid critical temperature for helium is 1.7 Kelvin, very low. But if you get it, it's a lot easier to pump because you basically just push it and it flies, to 27 miles around the ring and comes back. Yeah.
Would superconducting wire work in outer space? Because
yes, but it's not cold enough in outer space.
What?
Yeah. It's not that there's a sun around anywhere. If you're really in deep space, maybe you can make that work, but you would still need to actively cool it in general. And if you're near a spaceship or something, all that leftover heat would get into it. You still need to cool it. And it's tough because if you run out of helium, then what, right? So now there are these things called low temperature. No, they call them high temperature superconductors. High temperature is a relative term. It means liquid nitrogen temperature. Liquid nitrogen temperature is the key one. If you can get something that has a critical temperature at liquid nitrogen is so cheap. Okay, you get it basically for free because where do you find liquid nitrogen? Everywhere, right? It's even easier to find than hydrogen. So liquid nitrogen is really, really cheap. And if you could get a conductor that works well enough at that temperature, which we have a few, but you need to be able to mass produce them and stuff, then what can you make with superconducting magnets that are mass producible? You can make levitating trains. And you can already make levitating trains with magnets, like it's not a big deal, but superconducting magnets are much, much stronger. And if you only have to maintain them at liquid nitrogen temperature, it's not such a big deal. And then you'd be able to, run your high-speed trains a lot more efficiently.
But if your phone
And your hoverboards, of course.
If your phone falls on those tracks, it would be definition going.
Yeah, a lot of things. If you fall on the track, you too.
We eventually, if we get to the point where we can mass produce these,
What did you say?
if we get to the point where we can mass produce these superconducting wires very easily with the liquid nitrogen, if we have phones that only have
Okay, all right. Hey guys, quiet please. So tomorrow we'll wrap up. We'll wrap up the class. We'll try and do something to close everything together. I will hopefully have data for you tomorrow. Okay. So I'll see you then.
Let's tell Feynman stories until we die.